The first thing we had to do was make a motion diagram and the free body diagram. So on the left we have a free body diagram for the mass of 2, and on the right we have a free body diagram for the mass of 1. And for the mass of 1, the force of gravity is what we need to make our components for, because that's on an incline. So on the axis we drew our components, and we have the x component going to the right, so it's positive, and the y component's going down, so it's negative.
So here we have the net force equations. We have m1 x and y, m2 x and y. What we're going to be using is m1x and m2y because this is the way the tension forces are pulling to make the acceleration. So once you get these equations here, then you're able to use them and put them in a system of equations to solve the problem. Now, it might be a bit confusing as to why these two accelerations can be used. So that's why I just solved both for ft to show that these two are equal to each other. And if we want to, what we could do is set them equal to each other and then solve for the acceleration. But then there's the problem of the subscripts on a, like a1x and ay. But we can get rid of these because the acceleration is for the whole system, because the tension forces determine the acceleration for both of them, along with the gravity force in both 1 and 2. But the acceleration of the whole system would be the same. So I solved this system by doing elimination by addition of both of the systems, so that I came up with m1g sine theta minus m2g equals m1a plus m2a. And I was able to factor out the a from the right side to make it a times the quantity m1 plus m2. So then I divide both sides by m1 plus m2 to move it over to the other side, and I had just a equals m1g sine theta minus m2g over m1 plus m2. And that's the answer.